there's emissions, burn fossil fuels, there are emissions of air pollutants and greenhouse gases, mainly CO2. And as well as wastewaters, in particular in Texas, we do a lot of hydraulic fracking that also produce wastewater as well. Not many people maybe know that, but today, so I'm developing technology for both CO2 and water treatment. Today, I'm going to focus on the CO2 capture and conversion. And I will introduce the 3 approaches that I have worked on as listed in the title of my talk. The photocatalytic conversion process first, I conducted at room temperature or near room temperature, reducing CO2 with water with low intensity sunlight. Right? And the second topic is the photothermochemical process. Let me get this annotation. And this is conducted under concentrated solar condition at high temperature. The third one is, which I recently worked, is the electrochemical reduction of CO2. Hopefully then using solar electricity due to this recent dramatic drop of solar PV. And then I think this electrochemical approach is becoming more and more promising. So today I'm going to briefly introduce 3 of them one by one. Hopefully I can have time to do that. Please bear with me if I speak fast on some of these slides. So at the end, I hope to give a summary of these 3 and then have a comparison of their pros and cons and give my personal perspectives of this over the field of CO2 conversion. All right, let's see. First is photocatalysis approach. All right, so actually Mother Nature is doing this has been doing this a good job for a long time, right? And we know that fossil fuels actually come from this photosynthesis. However, we humans are consuming fossil fuels at a much faster speed than the Mother Nature can provide us. Okay, so since 1970s, people have developed this so-called artificial photosynthesis approach to produce solar fuels from sunlight. For example, here the heterogeneous using heterogeneous catalysis semiconductor nanocrystals like TiO2. So under photoillumination, if the TiO2 absorb photon energy greater than its band gap, then electron holes will be produced, and electrons go and reduce water into hydrogen, or if there's CO2, it can reduce CO2 into these various products. Meanwhile, the holes can oxidize water into oxygen. It sounds like a very appealing idea. However, there are several scientific challenges. First of all, the choice of catalyst. Right? As of now, even though several decades has passed since the first research, there is still no winner of a single semiconductor that can have the appropriate band gap, namely narrow enough to absorb a good portion of sunlight, and then the appropriate band edges that can power both the reduction and oxidation reactions. Right? And secondly is the fast electron hole recombinations, either happening in the bulk or on the surface. So that leads to a low yield, typically in the micromole per gram range. And then that means there's a long way before commercialization. Of course, other challenges include instabilities and toxicity and abundancy of the material and the product selectivity. So TiO2 is believed to be a very suitable or I would say widely extensively studied because it's abundant, cheap, stable, and non-toxic. But the main drawback is its large band gap. So it only absorbs UV light. So in the past about 13 years, I have worked on this photocatalysis for CO2 reduction and working with TiO2-based catalyst by doing a lot of engineering approaches, right, to modify TiO2 or forming some TiO2 nanocomposites, hopefully to overcome the above mentioned limitations. So here are those listed those approaches I've used. Many of those now become well known and well practiced. But today I hope to introduce something maybe that's not so common, and I think it's interesting. This concept, I call it integrated CO2 capture and photocatalytic conversion, and operate at the flue gas temperature. So actually, this was the main idea of my career, NSF career project. In the meantime, I would also like to introduce a couple of very useful in situ spectroscopy analysis tools for mechanistic study. This include in situ FTIR and in situ X-ray absorption spectroscopy. All right, so now if you're in the community of CO2 capture and conversion, and you probably know that this field is probably divided by two main areas. One is for capture and one is for conversion, and there are not many overlap between each other. When we do conversion, we typically use, of course, in the lab scale, we use a pure CO2, right, from a gas cylinder. But if we want to do this in a large scale for commercialization, then the more economical way is to directly convert CO2 emissions from, say, power plant flue gas, without the need to concentrating CO2. Because otherwise, when you do CO2 conversion, you have to include the cost of capture, right? So then if we examine for example, coal-fired power plant flue gas composition, we can see they're both CO2 and water exists there, which is good. Those are the reactants. And there are some other minor gases. And also interesting is you can see here the temperature is above 100 degrees Celsius. Right? And so then my thought was, can we integrate this CO2 capture and photocatalytic conversion process by designing just one hybrid material with adsorbent and photocatalysis components together, and then tune this catalyst so that it can operate at power plant flue gas condition. So by doing that, then you don't have to cool down flue gas for CO2 capture, which is typically required if you use amine-based sorbent. So no temperature will help adsorption. Secondly, you don't waste the thermal energy from sunlight. And again, conventionally, photocatalysis was conducted at room temperature or near room temperature. Right? So by shining at sunlight, you use the UV portion, but you discard the IR part. And then another time I have to cool it. So that's extra cost. So if you can run at this high temperature, higher temperature, and using sunlight, that's a perfect match. So lastly is by operating at a higher temperature, then we can promote the product desorption, which sometimes is actually a limiting factor, right, for these reactions. All right, so with that in mind, we have developed this hybrid magnesium aluminum layered double oxide material with the titanium dioxide nanocrystals embedded in between these interlayers. So this layered double oxide is derived from layered double hydroxide materials, and after calcination, it just become oxides. And then it turns out it has a good adsorption capacity at moderate temperature. So you can see these are the TEM images. These are the layer structure with TiO2 crystals embedded in the layers. And then interestingly here, if you look at the BET analysis, this hybrid material with 43% of the titanium dioxide exhibit dramatically higher surface area than the individual components, right, of them. So that means because of putting them together, it induced a lot of these small pores, so the surface area increased. And then here the TGA, adsorption isotherm tells us with the hybrid material also, has much higher CO2 uptake capacity, right, than the individual components. Okay, that's clearly see the synergy of this, adsorption. So now let's see how we do this process for the integrated capture and conversion. Okay, again, unlike conventional photocatalysis, which you shine the light, right, on in the photoreactor continuously, right, then you produce a product continuously. Here, what we do is we first do this in a dark condition, do a dropshing, right, for CO2 and water vapor at 150 degrees C, which is flue gas temperature. And then after some time, we just cut off CO2, and then we eliminate the sunlight. And in the meantime, we can tune the temperature. So for example, we slightly increase temperature to 200 C. So you can see in that case, it's similar to a temperature swim, right, absorption desorption process. So you can expect that part of the CO2 is dedropped, from the material, and because in the meantime we have photo illumination, and then CO, some of the products, major product is CO, can be produced from these dropped CO2 species, and ideally this material is automatically regenerated, right? And then we can go through this process, dark light process again, cycle over cycle. So before I show you the results here, I just want to introduce this in situ diffuse reflectance FTIR called DRIFTS study. So this drift cell, the uniqueness of this cell is it has a quartz window that can allow photo illumination. And meanwhile, this cell can be operated at a designated temperature, and then you can introduce your reaction and gas in and out of this cell. So on the right-hand side, you can see the IR spectrum of this, three processes. The first one is adsorption, right, in the dark. You can see a lot of these various carbonate, bicarbonate species form. And then we switch CO2 into the helium. Then what do you expect? And also just increase temperature to 200. You can see that part of the dropped species are desorbed, right? And then it reached actually an equilibrium. And then we keep the same temperature, but we just turn on the light, right, for some time. And then you can see these carbonate species are further, reduced, which means these, because they operate, those two and three are at the same temperature. So that means the UV radiation actually helped the desorption or some chemical reactions happening on the surface to convert carbonate species into CO. And so we quantified this amount of desorption and CO produced, and then we did cycle experiments. And here shows data for 5 cycles. If the total drop is 100, right? And you see for the desorption, 80% of these dropped species are desorbed during that process, and then 50% is converted into CO, and then about 5% is still on the surface as a residual. So considering the 15% is actually quite a dramatic number, because considering the huge amount of CO2 emitted from power plants, if we can really convert 15% of those into CO, that will be very interesting and very, very promising, right? So, but you can see one limitation here is after 5 cycles, the desorption capacity probably maintains the same, but the CO conversion decreased a bit and the residuals increased, which means cycle after cycle, it's kind of deactivating a little bit. So at one time, then we need to fully regenerate the material at a higher temperature after some cycles, because the 200 C is just mild. So you might need to say 400 C to fully regenerate to desorb those residuals. But that's not the the major limitation, but I think the major problem is the kinetics, this mismatch between these photo conversion versus adsorption or desorption. So the photo conversion is the pretty slow process, right? Takes a longer time than the desorption or adsorption desorption process. So which means if in a full-scale application, you might need to build a larger volume of reactor for photo reaction. So that kind of limit the commercialization potential. But nevertheless, I think that's a relatively new concept that we have developed. Okay, now I want to switch gear a little bit on this in situ drifts, in situ X-ray absorption spectroscopy is set up. I think this XAS is a very useful tool to study the structure or property performance relationships, right? But in situ photocatalysis study was rarely done. So our contribution is to design this type of cell. You can illuminate the UV, and then meanwhile with the X-ray, you can discover the change of, for example, in this case, the copper TL2 catalyst. We can see the change of copper valence if we begin with copper 2+. To begin with, this photoreduction process doesn't change the valence, right? But if we begin with copper 1, reduced copper species, the valence actually, the population of copper 1 decreased. But if we introduce host scavenger, then the population of copper 1 is maintained or even increased, okay? And so of course, here's XOF's analysis indicating this single bond of copper oxygen. All right, so we did some XOF fitting, and then which matched the Zane's analysis, and then also some quantification is done here and correlated with this catalytic activity. Copper 2+ is stable, but it's not reactive. Okay, copper 1+ is more reactive, but it is oxidized to 2+ by likely the photo-induced holes. So that's why this material is not stable. Okay, but then if we introduce host scavengers, copper 1+ is stable, and then it reaches the highest catalytic activity. So that's, I just want to give this example of how this in situ XAS can be a very powerful tool to correlate, right, the structure performance relations. All right, so let's see, move on to the second topic is the photothermal chemical CO2 reforming of methane. I think currently industrialized process is called the steam reforming of methane to produce syngas or hydrogen, right? And most of our hydrogen actually is produced from steam reforming. The benefit of doing CO2 reforming, or we call it dry reforming, is because you can fix more carbon, right? So that lowers the carbon footprint. So again, it shares the same, property like endothermic reaction, so it needs high temperature, right? And also there's a side reaction like gas reverse water gas shift, and also this side reaction of methane decomposition and Boulder reaction can cause a coke deposition on the surface so that the catalyst deactivates. This is the main reason, deactivation is the main reason that this dry reforming is not commercialized yet as compared to the steam reforming. Okay, so since I've been doing photocatalysis, right, for a long time, I'm thinking, oh, can we take advantage of this photocatalysis and incorporate that into the thermal catalysis, in this case at high temperature? The reason is because people have used solar energy to do this, concentrated solar. However, they just use solar as the pure heat source, right, when they do the concentrated solar. Then use conventional catalyst. So if I want to try to get a synergy of photocatalysis, I need to use a semiconductor as my support. So I chose cerium oxide, right, as a support. It's a photo catalyst with a band gap around 2.8 EV, and then of course TT is the thermal catalysis for methane decomposition, and meanwhile it's a co-catalyst for thermal catalysis. And then of course I include some promoter there. And this one also interesting, the AOD, atomic layer deposition of a surface coating of magnesium oxide. You can see after coating a very thin layer of a magnesium oxide, you can see the photoluminescence spectrum, is dramatically decreased, which means it can reduce the surface recombination. So here's a setup when we do the experiments, and we use the concentrated solar simulator, which can go up to 30 sounds of illumination. So here's how the reactor look like. Have the solar radiation about one inch square on this catalyst surface, and we used a tube furnace as auxiliary heating source if we need at a higher temperature, because solar itself can only reach about 500 C. So at higher temperature, we need more thermal from the tube furnace. Of course, as a control, we turn off the light and only heat up the reactor by tube furnace. Okay, here's some activity data for the production of hydrogen and CO from this PTC dry reforming. So you can see these solid markers are the dark condition, which means only the tube furnace is providing the heat, right? The open markers are light, so under concentrated solar. They both are operate at 600 C, the same temperature, because we tune that with the thermocouple, the temperature is controlled. And you can see the dramatic difference here. In the dark, activity is very low, and then it deactivates regardless of this, the materials, right? But with light illumination, you can see it's quite stable. And then by adding some, zinc promoter, and then it's more active. By coating just a 5-layer or AOD layer of magnesium oxide, it's much more active, right? So you can see actually here, this graph shows you we tuned the number of AOD cycles or the thickness of the overlayer. One cycle is, one atomic layer. It's less than 1 angstrom. So 5-layer actually is less than 0.5 nanometer. So it's sub-nanometer, but it has dramatic effect, on this activity. You see 5-layer is about optimum, but a thicker layer actually reduce the activity, maybe because it just inhibit the diffusion, right, of the reactants to the catalyst surface, and also prohibit the charge transfer under this solar. So there is an optimum layer. And also, some people may wonder if you have the photo effect, or it's truly a photo effect, photocatalysis effect. So we did control experiments using non-semiconductor like silica or alumina as the support. And we don't see that this promotion under light illumination. So it's light and dark the same, okay? That's more or less tells you this due to photocatalysis. And also we tried actually TiO2, because it's a semiconductor, but it doesn't work well. It showed a little bit of effect, but not very well. So cerium oxide is the best so far we found. I think because of this cerium, the oxygen vacancies or the mobilities of oxygen that plays a very important role. So we did a calculation of the cerium 3+ population, before and after reaction, right? This is through XPS. So you can see the fresh one is about 33%, and then if it done only in dark condition, the cerium 3+ population dropped significantly for all these materials, right? And then, however, if I've under light illumination, the population of cerium 3+ is maintained, which correspond very well with the the stability or the activity, right, of this the GC measurements. Okay, so with that, I think that demonstrate we have proved the synergy, right, between photo and thermal by probably more effectively use the full solar spectrum, the UV part or near UV part to power the photocatalysis, and then the longer wavelength part, right, IR including, to power the thermal, and then you have an overall higher efficiency. So also we have done some temperature dependence studies with this material. So we tried right from low temperature to high, and then we found that actually if you draw a horizontal line here to reach the same production rate of hydrogen or CO, right? So you can actually save about at least 100 degrees C if you operate under light compared to those in the dark. Okay, that's the first observation. And second is this photocatalysis effect contribution is more significant at higher temperature rather than at a lower temperature. This is very interesting. So we're still investigating the reason, but my hypothesis is here is maybe this photocatalysis promote more on the CO2 dissociation part. But the CH4, the methane dissociation, because it's mainly driven by the metal catalyst and driven by maybe a higher temperature. So that's why you need a higher temperature to dissociate CH4, and then the photo can kick in and then help the reaction of the intermediates of the CHX with the dissociated CO2. So that's why there's a sort of a threshold for the photo to kick in. All right, so this then to confirm that hypothesis, we used this again in situ drifts to study the surface property under real reaction conditions. Here, of course, we did only in 300 because at too higher temperature the spectrum are very weak. Okay, so nevertheless, at 300, you can see the left one is the dark condition, right is the light under light. So in the first few minutes, the spectrum looks similar, but under light, you see after 10 minutes also, the CO2 absorption peaks are different from that in the dark. And in the meantime, those two peaks, right, linear absorbed CO and gaseous CO are observed, okay, under light only, not in the dark. Okay, so which proves that this photocatalysis really activates reactants at a lower temperature. Okay, so that's the second part, and then now I want to maybe spend the last 10 minutes or so on the third topic. It's electrochemical CO2 conversion and diffuse, as I said, because of the dropping price of the solar or PV or wind energy. So it's becoming more and more economical to use this to do the splitting of CO2 in CO2 electrolyzer. And also in my research, of course, I focused on the CO again. Many other researchers are studying formic acid or C2C3 products. I worked on CO because I think it's relatively easier thermodynamically. It's not that challenging. It only needs 2 electrons and easier to separate the CO from the CO2 rather than you need to, if it's a liquid product, if you need to separate the liquid from the electrolyte, it costs more energy to do that, right? And also, again, it's an important feedstock as part of syngas. So, however, also challenges, including this slow CO2 reduction kinetics, the different selectivities, right? Which can also, the hydrogen evolution reaction compete with CO2 reduction. So for CO2 to CO, I think the state-of-the-art catalyst is metal, right? Like silver in this case. You can show this nanoporous silver. Also recently, people have used these 2D materials. And I'm interested in carbon. One reason is the carbon is earth-abundant material. And carbon itself, it's a lower price than metals. Of course, to fabricate those unique carbon structure, probably need some energy-intensive process to do that. But hopefully, we can develop a more, environmentally benign or low-cost process to produce this carbon material. So that's the goal I'm working on. right? So again, working on with carbon, we also need to look at these issues of overpotential, the current, the competitive hydrogen evolution. Okay, so to address these challenges, we are focused on three parts. One is doing some dopings on this carbon catalyst. Nitrogen is a well-known doping, but we're also looking to the other non-metal dopings like phosphorus, sulfur, and fluorine. The second approach is trying to increase the selectivity of CO by developing single atomic metal and nitrogen doped catalyst. And because we found that if you have metal clusters or nanoparticles, it favors hydrogen evolution, but a single atomic this metal catalyst favors CO production. Okay, so lastly, we have engineered also the surface of the carbon by creating more pores and edges, which we believe are the more active sites, and build some hierarchical structures, and in using some alternative carbon source, as I said, to lower the price. For example, we used commercial carbon nanotubes as the carbon source. We already used the petroleum coke waste as the carbon source to develop relatively lower cost carbon materials. Okay, I think here, so first we have examined or screened some these different metals, right, these transition metals, and see which one is, performs better, and then dope them with the nitrogen. So typically you form this metal nitrogen bonding. Typically it's metal nitrogen 4, okay? So this is through some simple synthesis process to get the graphene-like structure, carbon structure, just through the pyrolysis of some precursor of, say, citric acid as a carbon source, urea as the nitrogen source, and then the metal nitride as the metal source. Just pyrolyze them at say 900 degrees Celsius, then you can get this structure. Okay. Then we compared the activity in terms of Faraday efficiency of CO production. You see this volcano shape, right? So we can reach over 90% on the nickel. So we found by comparing these 5 metals, we see that so iron and nickel appears to be the winners. Iron has a good, not bad, close to 90% CO selectivity, but the drawback is it has low turnover rate frequency or low current. However, the overpotential is quite low, right? So that's the drawback of iron. But for nickel, it has also a good CO selectivity, more than 90%. But the downside is that it requires a little bit larger, overpotential, although the activity is high, right? So there's just different pros and cons for these different metals, but it appears that iron and nickel are more interesting materials to work with. Okay, then we in this work is we developed this single atomic metal nitrogen carbon catalyst through a interesting approach called using ZIF material as the precursor. This in collaboration with one of our project collaborators. So then we developed this ZIF material, and then through carbonization you get single atomic catalyst. So here this STEM images just show you from the far right, you can see here these bright dots indicates the single atomic, either here's iron or here's cobalt. Okay, and then the X-ray absorption analysis also tells you, right, the ZENS gives you the oxidation state, and then X-OFFs give you the coordination environment. So you can see this owning a single peak, major peak of this, metal nitrogen bound. There's no metal bound, which means though it's a single atomic. And then it is the coordinate number between metal and nitrogen is 4. So that confirmed it's iron M4 or cobalt M4. Okay, again, comparing the CO2 reduction activity, by evaluating the current and also the Faraday efficiency. Okay, you can see that iron is more active than cobalt. Again, that confirms with the previous study, but with this different morphology of carbon. Right. So iron can reach 93% selectivity. So despite both iron and cobalt catalysts, they have similar surface area and similar composition. So iron is more active than cobalt. Here, this figure also shows you the long-term stability is good, at least for 20 hours. It's stable. Okay. Again, we'll also have some collaborators working on the DFT calculations to review, right, the catalytic nature of this catalyst. And we found also interesting the edge-hosted, methyl nitrogen carbon species is more active than the bulk-hosted configuration. And so these calculations show you that if you see this table here, the overpotential, onset overpotential for iron, right, is lower, always lower than the hydrogen evolution. Okay, and then for this edge-hosted N2+2, it's even lower. Okay, so that means this is iron N2+2 is more active than the N4 structure. Then if you look at cobalt, then cobalt has, requires a higher, overpotential compared with iron. And also for hydrogen evolution, it, CO site is maybe favor hydrogen evolution. Oh, so that matches with the previously this selectivity, right? The Faraday coefficient of C of cobalt is only 45%. So that matches the theoretical calculation, in here. All right, again, also we did the nickel, and we said nickel is also promising, nickel, nitrogen, and carbon. So this work, we also provided single atomic nickel, nitrogen, carbon. We found 96% Faraday efficiency. It's very close to 100%. And then at a relatively, low overpotential, okay? So the current is here more than 10 milliamp per centimeter square for CO. I think the state of art is also around this range. So again, I want to, maybe I forgot to mention that all these activities is characterized in a 3 electrode system, right? With working electrode of the metal carbon catalyst, platinum as the counter electrode, and silver chloride as the reference electrode. Okay, so then again, after knowing that this metal and non-metal dopings, then we created another co-doping, iron and nitrogen sulfur co-doping all together. And you can see it's further, with the sulfur co-doping, it further increased the Faraday efficiency to 98%. And at a low overpotential of 40.49 volt. And then through the theoretical study, we found sulfur doping lowers energy barrier, right? And enhancing the interaction between the iron and these intermediates. Okay, so finally, I think for maybe 3 minutes to summarize these 3 approaches. Again, this table you see is only based on my own research. I've done on these 3 approaches. There are many other approaches, such as photoelectrochemical, PEC, which is also a very, very popular approach. I haven't worked with, but so that's why I didn't include that into the comparison. And for electrocatalysis, also there are some high temperature electrocatalysis I could use in molten salt, which is not that popular, but again, that's approach. I think just want you to know this is not inclusive, right? Just from my own experience, what I've done. Okay, so if I go through these pros and cons, probably one by one, you can see for photochemical or photocatalysis. In here, I use the gas phase CO2 to react with water vapor, okay? It's not in the aqueous phase for photocatalysis. I want to clarify that. Of course, there's, people use aqueous phase CO2 bubble through the electrolyte. It's more on the PEC approach. But in this photocatalysis using a gas solid phase, I think the biggest advantage is the lower cost, right? In terms of it's very simple, and so you just gas in and out, you get products. So cost is low, but the drawback is the conversion is also very low. Okay, and stability, as mentioned, stability is also low. Because of the low conversion, then you have the separation issue. You have to separate a very low concentration of CO from CO2, for example. Then that would be costly. In that sense, from the material side or the reactor point of view, it's simple. Okay, so then I come back to this potential for commercialization. I labeled it low to moderate. So for the high temperature approach of photothermal chemical, right, the advantage is that it's high conversion, right? High conversion and high selectivity. You get CO or hydrogen. Of course, that's a syngas you want, but both of them are at high yield. So, and then the minor, there's no other, pretty much no other minor gases produced. So you don't need to separate them downstream, okay? But the downside is that the capital investment is high because it's concentrated solar. High temperature, some material cost, right? And also installing, concentrated solar reactor, high cost, and also the solar tracking is an issue because for concentrating solar, you need high solar tracking. So, and also there's a limitation. You can maybe only do that in the southern area, but not in the northern area where you don't have a normal insolation of sunlight. So that's probably the reason the many industrial industry are not very fond of investing a lot of money to do this, probably because of the high initial cost and or some issue with some long-term maintenance. Okay, so I label the commercialization potential to be moderate. Okay, and then finally is the electrochemical. I said although now the conversion, although you see the high selectivity, but the conversion actually is relatively low. Of course, with the development of those flow cells, then the conversion is higher. So I label it low to moderate. So hopefully this efficiency can be increasing, in the near future. Okay. So of course it faces some separation costs as well. But the overall investment, I think it's low. And so it's moderate, but you have to apply PV plus, this electrolyzer. But PV price is going down dramatically. So that's why I label the commercial potential is moderate to high. So, okay, to conclude maybe, and you can see also that in recent years, I'm working more on this area, maybe because it has a relatively higher potential for commercialization. Okay, so with that, I want to conclude my talk, thanking my students and postdocs, and thanking my collaborators, and most importantly, thank my research sponsors, many sponsored by National Science Foundation and the ACS Petroleum Research Fund. Okay, with that, thank you very much for attention, and I'd be happy to take any questions you may have. Hello?
Dr. Li, you have questions in the chat box.
Okay, let me see if I can get that. I have to stop sharing to see that. Is that okay?
You can, yeah, you can.
Okay. That TEA analysis yet. So probably we plan to do that in the future, but not now. Haven't done that yet. Okay, same questions, wondering what was CO2 carrier to convert it to CO or other products. on the surface for the catalyst. So the first question, okay, the carrier, there's no, I don't know which one you're talking about. If the first one, there's no carrier, it's just CO2 itself. It's 100% CO2 to begin with, okay, during this photocatalysis process. Then of course you get less than 1% of CO, right? So that's why I say there's a need separation. If you mean that the integrated capture and conversion process is the first is CO dropship, the second one is using helium as a carrier gas to take the CO out. If that was the question you were asking. So for dry reforming, it's a CO2 plus methane. That's the reaction gas, right? Then you get CO and hydrogen as reactant as the products. Again, for electrochemical, it's also pure CO2. And then you bring the CO out from the CO2. So we measure CO from CO2. So did you dissolve CO2 in a liquid or was it flow of CO2? Yeah, it's the flow of CO2 bubble through the electrolyte. What's the efficiency? I'm not quite sure what that means. The efficiency of what? Okay, maybe move on to the next question. Do you think of Si or copper? Is that Si? What? Chloride catalysis for the thermal generation of hydrogen using neutrons from nuclear. That's 12% of energy mixed in the US. For soda, did you use iron oxide or both? No, the question is, it's a good suggestion. I haven't thought about this as neutron energy to do that. And no, I haven't used these iron oxides. I think a lot of people using this iron oxide for chemical looping process, if I remembered. But that is a little bit different reaction, right? You convert metal oxide to metal and then regenerate. So that's probably, it's another solar thermal technology. Actually, also people use cerium oxide to do that too. So, but that's the cycle between the metal and metal oxides. In my case, the dry reforming part is the catalyst stays the same, right? It's a stable catalyst. So it's a different approach, but this is a good suggestion. So next question, TiO2 or alumina as support, any try out on other support? I think if you mentioned about the dry reforming or TiO2 or alumina as support, yes, I think I briefly mentioned that in my talk. Maybe I spoke too fast. We tried aluminum oxide. There's no, the activity is very low. And also the difference between light and dark is almost no difference. For TiO2, we tried out as well as the support. There are a little bit increase of activity under the light illumination, but not much. So that's why I think it's a cerium. Why cerium is good is the oxygen, all right, the vacancy is you have cerium 3+. You form, actually cerium 3+ may reduce CO2, right, into CO, and then you create cerium 4+. And then the photoillumination could, the electrons from the photo will reduce 4+ back into 3+. So to maintain that process, to like keep this reaction going. So the cerium 3+ may be the active sites. So that's my hypothesis to explain this. And why TiO2 is not good. TiO2 is not doesn't have that much oxygen vacancy and mobility. Okay, do you know the next questions? Do you know the reason for the deactivation of magnesium and TiO2 catalyst during the CO2 desorption step, during the CO2 adsorption step? I think it's because the low temperature, because you see the first cycle we have 5% there already. So the 200 degrees C is really not it's probably too low to desorb all these carbonated species. So even if you don't shine light on it, I would expect that you get only 2 parts, right? Desorb CO2 and the residual. So then your residual will still increase. Even if there's no light, you see. So that I think the reason is the desorption temperature is just too low. You know, as I mentioned, then now and then we could, you know, regenerate at high temperature, and hopefully the activity will come back. So I don't know if that addressed this question. Okay, next question is, I wonder why copper oxide was not reduced to copper 0. Okay, great question. So this one is because we used copper 2+ to begin with, and then we used, I think, hydrogen reduction at mild temperature, only 200, and then at, I think, atmospheric pressure. Okay, so in that condition, it's very difficult to reduce copper 2+ into you know, 0-valent copper. That's why we also, when the XAS study doesn't show any in 0-valent copper. Okay, so I think there are researchers, they do, you know, very high temperature reduction, right? And then this high pressure, you know, then it might give you the copper 0. But again, it's also very challenging to get a pure copper 0. It's always sometimes copper 0 and copper 1 mixture. And that's why the reason when you do XPS, you typically, you cannot distinguish between, right, 0 and 1+, if I remember right. That's another advantage of using XAS from XP compared to XPS. And also another challenge is when you get your sample out from the reactor, the copper, we see that immediately the copper color changes. That means, right, it can be, the reduced species can be oxidized, you know, by air, you know, very quickly. So when you do this ex situ analysis, it's not accurate to characterize this copper species. Okay, next question. Concentrated solar radiant was used for PTC. Is it necessary? What about UV? Okay, I think the reason we use concentrated solar is because, of course, in real application, that's the solar is the source, right? To have that high intensity, and then you use concentrated solar. Of course, you can use one sun condition without this right, one sun, but you cannot reach high temperature using one sun condition. So idea is to using the solar to power the reaction, you know, at high temperature, and then in the meantime, the low wavelength UV part can, you know, synergize these right, the photo and thermal effects together to promote the overall reaction. So yeah, I mean, you could use UV or concentrated UV if you have a source of the UV. That's also doable, but in the meantime, you have to heat up the reactor by some other source, right? Or fossil fuel maybe doesn't make much sense, you know, because you produce CO2 as well. So again, you know, concentrated solar provide both the energy source. So any strategy to achieve the control over the edge or bulk host? Yes, we have, I didn't present, one of our recent papers used some etching, right, like hydrogen peroxide to etch the surface and to create pores. So we found that's one, you know, approach. We can do that, and there are other chemical or physical approaches, right, to produce the defects on the carbon surface as well. So this question is, in electrochemical CO2 reduction on metal M4 catalyst, how do you decide optimum pH? No, we didn't tune the pH. We just used right 0.1 mole or 0.5 mole potassium bicarbonate. So that's it's near neutral pH. In the non-aqueous solvent, no, we didn't do any non-aqueous solvent. It's just as a potassium bicarbonate as the electrolyte. The next question is, how about Ph.D. onto serum material to get directly to formic acid? No, I haven't thought about. We didn't work with Ph.D. and formation of formic acid. I don't know at this high temperature. I wonder if still get formic acid, right? Because the temperature is above, we showed it's above 700. So at that temperature, probably CO, right, is the product. So of course, if it's a low temperature, if you operate at a low temperature, then yeah, could be formic acid formation. Actually, we found, also didn't show this, is we did FTIR, in situ FTIR on our catalyst surface. We found formate as the intermediate at low temperature, right? Like say 300 or lower 200. But at too high a temperature, I'm not quite sure, because we don't see those peaks very prominently. But I agree with you. There's at least we see formate species on the surface that could be intermediate for CO. So if there's a way like another catalyst to promote, the formic acid production, that's possible. Okay, next, in Quebec, you can reach 6.08 cent Canadian dollar per kilowatt hour from green electricity. Yeah, great. Thank you for letting us know. That's pretty cheap. It's much cheaper than what we're now paying for, right? Our utility bill, I guess we pay 12 cents US dollars per kilowatt hour. So this is just half of it. That's fantastic. Okay, I guess did I cover all the questions? And if there's any other questions you'd like to ask, or you could always email me. I'd be happy to answer any questions you may have in the future.